and welcome to the second video in amount of substance. Today we're going to be looking at the ideal gas equation. So by the end of the session we should be able to recall the ideal gas equations. The next bit's really important for this equation. It's being able to convert the units into the SI units for the ideal gas equation and perform calculations using the ideal gas equation. So this video is mostly going to focus on looking at some worked examples and some exam questions about how to apply the ideal gas equation. Okay, so first of all, the ideal gas equation is PV equals nRT, where P is the pressure, V is the volume, N is the number of moles, R is the molar gas constant, and T is the temperature. Those all important SI units. So pressure is measured in pascals, volume is measured in meters cubed, N is measured in moles or mol, and R is the molar gas constant, which takes the value 8.31 joules per Kelvin per mole, and T is the temperature measured in Kelvin. Really important that we get those units right. The next slide we're going to look at shows how we can do some of the more common conversions for each of these. So pressure needs to be in pascals. You will often get answers given to you in kilopascals. So to convert a kilopascal into a pascal, you need to times it by 1000. Remember, the prefix kilo means 1000, or kilo means 1000. Just think like a kilogram is heavier than a gram. A kilometre is further than a metre, so therefore, just remember it's times by 1000. Volume needs to be in meters cubed. You'll frequently be given it in centimetres cubed. To convert from centimetres cubed into meters cubed, we need to divide it by 1,000,000. Okay, but you may also get given decimeters cubed, which is a common one. So to go from a centimetre cubed to a decimeter cubed, you need to divide by 1000. To go from a decimeter cubed into a meter cubed, you divide by 1000 again. So to go straight from there to there, you divide by 1 times 10 to the 6, or 1,000,000. N is the number of moles. Moles we can calculate using mass over mR, or concentration times volume, and we can look at that later, but in terms of the units it's just mole. R is always 8.3, and T is the temperature in Kelvin. What we need to realise with Kelvin is that 273 Kelvin equals 0 degrees Celsius. Okay, 1 Kelvin is the same as 1 degree Celsius, so therefore to convert degrees Celsius into Kelvin you just add 273. Okay, let's take a look at an example question. So calculate the volume, that 0.500 moles, so that's N, of an ideal gas occupies at 50 degrees Celsius temperature and a pressure of 100 kilopascals. So the way I like to do this is I like to do PV nRT, because we're going to be using our equation PV equals nRT, and then just extract everything that we need from the question. So the pressure is 100 kilopascals, which we need to convert to 100,000 pascals. So we've just times that by 1000. The volume is what we're being asked to calculate. So the volume is just going to remain V, or question mark. N, we know N is 0.5 moles because we were told that in the question. R is always 8.31. And T is 50 degrees Celsius, which again we need to convert into Kelvin. So we add 273 to this, which gives us 323 Kelvin. Okay, so just going to go up a little bit here. So PV equals nRT, which we need to rearrange in terms of the V, which is volume. So I'm just going to divide both sides by P, gets rid of P on the left and puts P on the bottom. So V equals nRT over P. And then I just pop these numbers in. So N is 0.5, R is 8.31, T is 323, and then I'm going to divide that by the pressure, which is 100,000, and then we should get an answer out in meters cubed, which is 0.0 134 meters cubed. Okay, let's take a look at some exam questions. Question 1. An alkene D is a liquid at room temperature and pressure but can easily be vaporized. When vaporized, 0.188 grams of D produces 82.5 centimeters cubed, that's our volume, of gas at 101 kilopascals, that's the pressure, and 373 Kelvin, that's the temperature. Determine the molar mass, MR, and molecular formula, so we've got two things to do. So that's the molecular formula of alkene, and it's an alkene D. Okay, so we've been given the mass here, and we're being asked to calculate the MR. Now, we should know that number of moles equals mass over MR. So if I'm being asked for the MR and I've been told the mass, but I don't know the moles, essentially in the PV equals nRT equation, I'm trying to calculate moles. So that is going to be the thing that I don't know. So let's do what we did before. PV equals nRT. So pressure is 101 kilopascals, which I times by 1000 to get it into pascals. Volume is 82.5 centimeters cubed. Remember, to convert from centimeters cubed into meters cubed, I divide it by 1,000,000. So divide it by 1 times 10 to the 6, which gives me 8.25 times 10 to the minus 5 meters cubed. N is what I'm going to be calculating, so that's just N. R is 8.31, and T, be careful, they've already given it you in Kelvin, so we don't need to convert it again. So that's 373 Kelvin. Okay, so write my equation out. PV equals nRT. Rearrange, I'm getting it in terms of N, so N, so I divide both sides by RT to get rid of it on this side, and it puts it on the bottom and the other side, equals PV over RT. So then I just pop my numbers in. 101,000 times 8.25 times 10 to the minus 5, all divided by 8.31 times 373. Put that into your calculator and you should get the number of moles to be 2.688 times 10 to the minus 3. Leave that in your calculator, okay? Because now we're asked to calculate the MR. So number of moles is equal to M over MR. So I now know the number of moles, it's not 2.688 times 10 to the minus 3. I know the mass is 0.1881. So therefore, I can work out the MR. Okay, so I just need to rearrange this equation. So I'm just going to swap the N and the MR because I'm dividing. So MR equals M over N, which is 0.1881 grams from the question, divided by the number of moles. Leave the full number in your calculator from previously, will give you a more accurate answer, and you should get 70.0 to 3 significant figures. Okay, so that's the MR. The next job was to deduce the molecular formula for this. So we're looking for an alkene, which is CnH2n, with an MR of 70. We know carbon is 12 and hydrogen is 1. Obviously in the formula, for every 112 we're going to have 2 N's. So we're looking for something which adds up to 70, which is C5H10. 5 times 5 times 12 is 60, and then 10 times 1 plus the 60 is 70. So our two answers are 70.0 to 3 significant figures and C5H10. And here's the mark scheme. So you've got 1 mark for rearranging the equation, 1 mark for substituting in the values, 1 mark for converting the units. The 4th mark here is for calculating the molar mass, or MR, and the 5th mark is for the correct formula being C5H10. Question number 2. A student determined the relative molecular mass, MR, of an unknown volatile liquid Y in an experiment as shown in the diagram. The student used a hypodermic syringe to inject a sample of liquid Y into a gas syringe in an oven. At the temperature of the oven, liquid Y vaporized. The students' results are shown in a table on the next slide. So we've got the syringe, we've got volatile liquid, it's being passed into a gas syringe, so we're collecting the volume of gas, and we've got an oven here. Okay, so massive hypodermic syringe before injection, massive syringe after injection. So obviously this is going to tell us the mass that went into the oven or into the gas syringe. We've got the oven temperature, we've got the pressure, and we've got the increase in volume of gas. So we're assuming that the gas syringe was on 0, and then afterwards it provided that value there. So define the term relative molecular mass. That's part 1. Use the experimental results in the table to determine the relative molecular mass of Y. The gas constant is 8.31. So we'll look at this part first. If you want to pause the video at this point and have a go at it yourself, that would be a really good idea. See if we get the same answer. Okay, so we're going to go through this again. So we're being asked to calculate the MR. So we've been given the mass here, which we're going to need to use in a minute. We've got the temperature, we've got the pressure, we've got the volume. So we're basically being asked to calculate number of moles again. We always have R. So let me just scroll this up. So P, V, N, R, T. So the pressure is 102 kilopascals, which is 102,000 pascals. The volume is 85 centimeters cubed, which I need to divide by 1,000,000 to get it into centimeters cubed, which is 8.5 times 10 to the minus 5. N is what we're trying to calculate. R is 8.31, and T is the temperature of the oven, which is 98.1 degrees Celsius. So I need to add 273 to that, which gives me 371.1 Kelvin. Okay, now I need to know N. So N equals PV over RT equals 102,000 times 8.5 times 10 to the minus 5 all over 8.31 times 371.1. That gives me an answer of 2.811 times 10 to the minus 3 moles. Okay, so I've been asked to calculate the MR. So N equals M over MR. So MR equals M over N. So the N is what I'm using from here. To calculate the mass, I need to subtract 10.7 away from 10.9. So this was the mass of the liquid before, this is after, so therefore we know that the mass must have gone in is 0.21 grams. So I'm going to do 0.21 grams divided by 2.811 times 10 to the minus 3. And that should give me my MR, which is 74.7. Right, so that was the second part of the question. We were also asked to define the relative MR, relative molecular mass. So we just need to memorize that definition. So the one that I use is the average mass of one molecule divided by 1/12 the mass of an atom of carbon 12. Okay, so that's the definition. I nearly forgot to do that. You mustn't forget to do that too in a question. If they give you two parts to one question, always make sure you do both. It's always worth just going up and checking the question again. So part B. Some of the liquid injected did not evaporate because it dripped into the gas syringe nozzle outside of the oven. Uh-oh. Explain how this, so give reasons why, how this would affect the value of MR, of Y calculated from the experimental result, and we can see it's going to be worth 2 marks. Okay, so we need to say how the value of the MR is going to be changed. Is it going to be increased? Is it going to be decreased? Or is it going to stay the same? And then we need to explain, so give our reason why. So it's a 2-mark question, so we need to say 2 things. So if the liquid, which is in the hypodermic syringe, which is injected into the gas syringe, essentially makes its way out of the syringe, but it doesn't make its way into the gas syringe, the mass that we write down, because remember the mass that we're recording is we're weighing the syringe with the liquid in it, and then we're weighing the syringe afterwards. So the mass that we're going to record is going to show that the liquid has been delivered, except it hasn't gone into the volume. So the volume is going to be smaller than we expected. Okay, so the volume is going to be lower than expected. Right, but with the same mass, the mass being the same recorded, the mass is the same recorded, which ultimately is going to have what effect on the MR? So where is our volume? So our volume is up here in the equation. So if we've got a smaller volume here, the number of moles that we record is going to be smaller. So ultimately, when we come to work out the MR, we're dividing by the N here. If number of moles is smaller, then that's going to make the MR larger, because if we divide by a smaller number, we get a bigger number. So therefore, the MR would be greater. Okay, let's have a look at the mark scheme. So we've got 74.7 is the mark scheme, is the answer. The two definitions are there, either of which are fine, and the lower volume would be recorded, therefore the MR would be greater. Okay, next question. Again, maybe you have a look at this one. We can come back to this in a second. Okay, so a sample of pure MgNO3 was decomposed by heating as shown in the equation below. A 3.74 times 10 to the minus 2 gram sample was completely decomposed by heating. Calculate the total volume, so that's what we're being asked to do. So volume is the question mark. Of gas produced at 60 degrees Celsius, temperature, 100 kilopascals, pressure. Give your answer to an appropriate number of significant figures. An appropriate number looking at all the data, so 3 sig figs, 3 sig figs, 3 sig figs. So an appropriate number is going to be 3 significant figures. Okay, so we know the mass. So that means if we know the mass and we know the formula, we therefore know the moles. So we're going to know the moles of this, which is MgNO3. Okay, so our first job is to work out the MR of MgNO3. So we go to our trusty friend, the periodic table. We find that Mg has an atomic mass of 24.1, nitrogen is 14, oxygen is 16. We pull all of that into the formula, so it's 1 magnesiums, it's 2 nitrogens, and it's 6 oxygens because of the 3 times 2, which gives us an MR of 148.1. So the second thing that we now need to do is work out the moles of MgNO3 which is mass over relative formula mass. So the mass they told us was 3.74 times 10 to the minus 2, which I've got from there, and dividing that by the MR, which I just calculated here, which is 148.1, and that is going to give us an answer of 2.52 times 10 to the minus 4. Okay, so we now need to have a little bit of a think. So I've got the moles of MgNO3, but I've been asked to calculate the total volume in centimeters cubed of gas produced. So it's really important that we look at the state symbols. And I always say, if they give you state symbols in an exam, there's a very high chance that it's going to be really important to the question. They won't always give state symbols. So the state symbols are here because we've got a solid making a solid and a gas and a gas. So the total gas is 4 NO2 and 1 oxygen. So the total moles of gas produced is 5 moles of gas. Okay? we just calculated the moles of magnesium nitrate, and there are 2 moles of that, so the molar ratio is 2 to 5. Okay, so how do I convert a molar ratio from 2 to 5? The way I always do this is I look at the number that I've got here, so it's 2, divide by 2, that gives me 1, and then I times it by this number, which is 5. Okay, so I need to take my answer from before, which was 2.52 times 10 to the minus 4, and then I'm going to divide it by 2 and times it by 5. Divide it by this number, times it by this number, which gives me 6.313 times 10 to the minus 4. Leave these numbers in your calculator. So now I know the moles, the total moles of gas. So I can do my PV nRT. Okay, so the pressure from the question is 100 kilopascals, which is 100,000 pascals. The volume is given to you in the question, and it is, that's what we're being asked to calculate. The number of moles we just worked out to be 6.313 times 10 to the minus 4. R is the molar gas constant, and T is what they've given to us. It's 60. Remember, we need to add 273, so it's 60 plus 273, which equals 333 Kelvin. So we're being asked for the volume. So PV equals nRT, so volume is nRT over P, which is 6.313 times 10 to the minus 4 times 8.31 times the temperature, which is 333, divide that by the pressure, which is 100,000, which equals 1.75 times 10 to the minus 5. If we look up at the question, it says calculate the total volume in centimeters cubed to an appropriate number of significant figures. Well, this is 3 sig figs, but this is in meters cubed. So to convert it into centimeters cubed, we need to times it by 1,000,000. So it's the opposite to what we've been usually doing, which will give us an answer of 17.5 centimeters cubed. Let's check. Have we done everything that the question said? Calculate the total volume in centimeters cubed given to 3 sig figs. Yes. B. The mass of magnesium oxide obtained in this experiment is slightly less than expected from the mass of magnesium nitrate used. Suggest one practical reason for this. So in other words, why has this not produced as much of this as it might be expected? The usual answer for this, it's got to be a practical reason, is some of the mass was lost on weighing. Okay, so some of the mass would have been lost on weighing, or because we've got a couple of gases, there's a very high probability that some of the gas would have blown away some of the product, so we're not going to have quite as much product. And here is the mark scheme. It's an extended response calculation, which means there are different stages. If you get right through to the end, it's 1.74 times 10 to the minus 5, which converts to 17.5 centimeters cubed. It could be 17.4 if you rounded intermediate. I always suggest that you leave the number in your calculator, but if you did get 17.4, you'd still get full marks because you've rounded earlier on. And then we've got some of the solid is lost in weighing the product. Okay, I'm not going to go through this example because I feel like this video is long enough, but you have a look at this question here, try and answer it, and I'll put the mark scheme on and I'll give you a few tips. So hopefully you've had a go at it. What I will say is a sample of boron oxide was reacted completely with carbon and chlorine. The 2 gases produced occupied a total volume of 5,000 centimeters cubed, so that's the volume. Pressure is 100 kilopascals and the temperature is 298 Kelvin. So we've got to convert that, so we have to divide that by 1 times 10 to the 6, and we've got to times that by 1,000 to convert the pressure. We've been asked to calculate the mass of boron oxide that reacted, So the first thing we need to do is calculate the moles of gas here. So calculate N, and we need to go back and work out the mass of boron. So the total moles of gas here are 5. The moles of boron oxide is 1. So first of all you need to do PV equals nRT to calculate moles, which is PV over RT. And then once you've got the moles of all 5 moles of these gases, you need to divide that by 5 to get this, and then you can calculate the mass. Here's the mark scheme. First mark is for converting pressure and volume. Second mark is for rearranging the equation and substituting the values in. Third mark is for calculating the moles of gas produced. The fourth mark is for therefore working out that you divide it by 5. The fifth mark, the fourth mark rather, is for timesing it by the MR, which is 69.6. And the fifth mark is for 2.81 grams. No other answer will be allowed because it's underlined. So if you make a mistake, if you don't divide by 5, you're going to lose 2 marks, which is pretty standard, okay? So that brings us to the end of the video. Hopefully we can recall the ideal gas equation, PV equals nRT, convert units into SI units to use in the ideal gas equation, and we've looked at a few example calculations using the ideal gas equation. Again, thank you very much for listening. I do hope this video was helpful. Thank you very much. Goodbye.